Miller's talk, he mentioned how these models of these quantum models of stochastic processes can be generalized to input-output processes. And if we remove the question of intelligence from the problem, then this can be seen as a model of an agent. So you can see an agent takes in some stimulus, based on some strategy that it has, will do an action to achieve some goal. And obviously, if it wants to be effective, it needs to have some memory of what it's seen before and what it'll do after. And so to execute a particularly complex strategy, generally it's going to need a lot of memory, and this is going to be some kind of penalty. And so the question is, what's the most efficient way to implement a given strategy? And it turns out, unlike a lot of these quantum advantages that have been found before, in this case, it's not that we have found a better quantum model than the best known classical one, but the best known classical one is the best possible classical algorithm. And so in this sense, our quantum advantage is absolute. It's not subject to being beaten by some superior classical algorithm. What we have is the case of we have a quantum advantage. We want to know how good we can make this advantage. Yeah, as Miller said, we can always beat these classical models, but we don't know the best quantum model. So the work that we've been doing, funded by FQXi, is to really study how good can these quantum advantages be, how much of a difference can we get. And so starting from the most sort of general possible quantum model, we've gradually whittled down the quantum features that help us in saving memory and the quantum features that don't. So that is, we start with some general state for the memory, some general state for the input, and whatever blank tape it wants, and let it output whatever states it wants for the updated memory, whatever it wants for you to be able to extract the output, and some junk. And so the way these quantum agents work, it's all covered within this kind of global unitary here. So at each step, memory comes in, we put in our input and some blank tape, out pops the output and whatever it discards, and the memory goes through into the next step, and that comes in on this side. And when I talk about memory here, I'm talking about the information cost in the sense of Shannon or von Neumann. But a lot of these results can be generalized to dimension, just with slightly less ubiquity. So we've kind of done a quite exhaustive treatment of these quantum models. And a few of the kind of key facts we've found so far, first of all, is that the memory states of the agent never need to be mixed, so we can always consider them to be pure. And for those of you who are familiar with Jim Crutchfield's computational mechanics, they're also in one-to-one correspondence with the causal states of the optimal classical model. Perhaps even more interestingly, one of the kind of typical examples of why we would expect these quantum models to be better is that if you measure a qubit in 2 different bases, you need 4 states to store this, so you'd need 2 classical bits, whereas quantumly, clearly, if it's just measuring a qubit, you only need a qubit. You might expect that being able to measure in multiple bases would provide you with some advantage. It turns out you don't, and same for the inputs. So coming back to this picture, these inputs are just the classical inputs, and these outputs are just measured in the classical basis. There's no need to do any POVMs, no need to have any rotated bases, just everything purely classical. And perhaps even more interestingly is that this junk has to exist. So in the case of the passive processes, we know we can always do things unitarily. So in the passive processes, no input, so you just have memory and blank tape, and out comes memory and output. But for input-dependent processes, we always must have this junk. Now, this junk contains no useful information. Given that we know the memory state that went in, the input, and the output, then this junk is fixed. It contains no information, and yet despite that, it still has to be there. And so our models still have to dissipate things to the environment, and this is unavoidable for any quantum agent. This isn't just a specific model. Any quantum agent has to dissipate in general, unless it's a special case of the process. And yeah, so this junk, despite being fixed, is actually the only degree of freedom in the model. Once you fix the junk, the rest of it's all fixed. Okay, so as I said, we know quantum does better. How much better can it do? So we have a systematic way of constructing things. And so here we have an example process where we can scale up some degree of freedom, here a time step. And so effectively, we're increasing the precision to which we're looking at our process. So classically, as we go to a high level of precision, so that's reducing the time step, the complexity goes up, the amount of information, as do the proof of principle quantum models from Miller's earlier paper showing this works. But once we actually go to these ultimate limits, we find that we can get a bounded quantum model. So the scaling advantage grows unboundedly. Yeah.